plug the output of one into the input of the other. And
So,
give you equivalent values.
Compositions.
So if you take the composition, what do you get?
X.
F of g of x equals g of f of x, and they both equal x. Because if you take an input, you put it into a function, you get that output. Taking that and putting it into the inverse should always give you back the original input, right? The inputs of a function are the outputs of its inverse and vice versa. So that means that if we compose these two functions, if they're inverses, I should get x, yeah? So let's see, f of g of x is equal to f of 2 to the negative x, yeah? Just writing it that way is a little easier to work with than the fraction. And then, well, f of x says take 2 and raise that to whatever your input is. So we have 2 raised to the 2 to the negative x power. And what we want to know is that equal to x? Well, on the left side, we don't really have anything to simplify that, right? Which is kind of our first clue that they're not equal. But, I mean, it's possible that maybe we just don't know how to simplify it, and there's some magical way that it could be equal to x. So if we're not sure and we can't simplify the left side, what do you think the simplest way to figure out if that's true is?
Can you just like look at the graph and see that like 3 and 1/8 is the same as like all of the numbers are just flipped on the two like tables?
It would depend on if that information would mean that they were inverses or not. Which we'll get back to. But right now, let's be right here. How can you tell if two things are true? If you have no way of simplifying either of them.
Plug 0.
Plug in a value.
Yeah, I mean, just plug in a number, yeah? I mean, I probably wouldn't use 0, only because 0 has a lot of special cases, right? Like, there's a lot of things that work nicely with 0 that don't actually work with other things. And so I usually avoid like 0 and 1 just because they're kind of special numbers that behave a little bit differently than others. So sometimes when something's not true, it'll end up looking true. It's like the number 2. I can say that 2 times 2 is equal to 2 plus 2, which is equal to 2 squared, but 3 times 3 is not equal to 3 plus 3, and also not equal to 3 to the third, right? Like some numbers just like funky things work out nicely. So let's try something. Let's be like, okay, if I take 2, like on your calculator, if you do 2 raised to the 2 to the negative 5, is that equal to, not x, 5?
No.
It's not.
No.
Totally not. In fact, this we can simplify. It's, you guys are going to love this. This is the 32nd root of 2. Right? Do you see it? Because 2 to the negative 5th is 1 over 32, right? Right, like if we were to write that as a fraction, it'd be 2 to the 1 over 32. And remember our radical rule, right? The denominator is the index. I mean, we could do that with the x, but it gets all sorts of wacky as far as like what the actual index is with the variable there. But it's definitely not equal to 5. I think we can all agree on that. Yeah, you probably got a really tiny number. So are they inverses?
No.
No matter how badly you would like something to be true based on whatever random thing pops into your mind, if it doesn't satisfy the definition, then like one of the most important things in math is not trying to force things. It's really easy to try to force things to be true that really seem like they should be true. But these are not inverses because they don't satisfy the definition. Once again, this property right here is like the most important thing that you can know about inverses, is that if you compose them, you get your original input back. Now, as far as the table goes, what the table shows us is that they are reciprocals of each other. So, right, like if I plug in -3 to F, I get the reciprocal of the output if I plug -3 into G. But do you guys remember when we did a table for inverses? Like that when we first graphed them, we had like 2 tables, right? What did we do with the X and Y values when we made the table for the inverse? We swapped them, right? Like if X was 1 and Y was 2, then for the inverse, the input would be 2 with an output of 1. So if we look at this line right here, that tells me that if these are inverses, an input of 2 should produce an output of 1. But here, an inverse or an input of 2 produces an output of 1/4, right? So it's true that these are reciprocals. They have actually some really cool, like a really cool relationship with one another. Like there's things that can be gleaned from their relationship to each other. They just don't happen to have an inverse relationship. They're just not inverse functions because they don't undo one another. This is important because tomorrow we will talk about the inverses of exponential functions. And so we want to be really careful to distinguish between inverses, reciprocals, etc. Opposites, which would be when we flipped it over the x-axis. Yes?
Can you tell me again how you picked 5 or how you got?
Oh, I just picked a number. Like any number. So like, I wanted to know if this was true.
Right.
So like, I just like picked a number and happened to pick 5 and put a 5 here and a 5 here.
And if the 2 to whatever came out as 5, then they would be in.
It would give me hope. So, I mean, it's funny, people sometimes are like when there's no solution or something like that, people are like, oh, I did all that work to find nothing out. Whereas, actually, it's often more helpful to find that something's not true. Because for a statement to be true, it has to be true for every single number I can possibly plug in. Which means if I plug one number in and it's not true, I can be like, oh, it's false. But if I plug one number in and it is true, that hasn't proved that it's true for every single number, right? So at that point, you would like try some other numbers, maybe. I'm not going to give you guys like something super wacky where like it's true for like 792 different values, but not true for like 3. But because that wasn't true, I completely gave up hope that that statement could possibly be true. And 5 just came out of nowhere. So I just picked a number.
Is the reflection over the x-axis a inverse or a reciprocal?
It's a reciprocal.
And this is also a reciprocal?
This is a reflection over the x-axis.
Oh yeah, the y-axis rather than the x. So either
Oh, I'm sorry,
the y
x-axis.
or-
No. Sorry.
I said x-axis.
I'm backwards. The reflection over the x-axis is the opposite.
Is the opposite, but it's not an inverse, and it is not a reciprocal.
That is
It's
correct.
just a symmetrical relation.
It's the opposite y values, whereas the reciprocal is the opposite x values.
On the
And
y-axis.
I mean, but be careful. Like, it's a reciprocal when it's exponential functions, a reflection over the x-axis does not mean anything about taking the reciprocal of anything,
Just for exponential.
unless
For now.
the input is as an exponent. It's the fact that the sign of the x value changed that made it reflect over the y-axis. And it turns out, because of properties of exponents, that makes these reciprocals, right? That 2 to the x is the reciprocal of 2 to the negative x. Whereas if I did like y equals 4x and y equals negative 4x, that's also a reflection over the y-axis, but those are certainly not reciprocals of one
For
another.
different reasons.
Right. Well, for the same reason, because we use the opposite input. But using the opposite input did not create a reciprocal in that situation.
Okay.
Okay, let's look at properties of these graphs. What is the domain of an exponential function? So, I was just grading your guys' corrections for test 3 that had a bunch of domain questions on it. And as I was grading the corrections, I noticed that a lot of people were talking about graphs, which I think is probably because it's something concrete that we can see. But when you think about domain, what you really want to be thinking about is like the operation that you're performing and like what numbers you can do that with. It's kind of an open-ended question to be like, what number can I do this with, right? There's like an infinite number of options. But really, every single operation that we work with, if you think about whether or not you can perform it on negative numbers, positive numbers, or 0, that will answer all the questions you need to about restrictions that it might have. So when we look for the domain of an exponential function, we're like, okay, what numbers can I have as an exponent? Because that's what our input is here, right, is an exponent. So whenever somebody says, what is the domain of this function, you want to think about the operations that are in the function and then ask yourself, can I do that with negative numbers? Can I do it with 0? Can I do it with positive numbers? So, can I have negative numbers as an exponent?
Yes. Yes, you can.
Sure. We just did, right? We raised 2 to the negative 3rd power. Can I have 0 as an exponent? Can I have positive numbers as an exponent? Done. What's my domain? All real numbers, because there's not a restriction on any of those. So my domain is all real numbers. And we see that from the graph as well, right? That we have an arrow going left and an arrow going right. What about my range? What's my range going to be? Really?
Because you have a horizontal asymptote,
Mhm.
don't you?
Mm-hmm. Luke, what's up?
Be greater than 0.
Yeah, it has to be greater than 0. Good. We can ask ourselves, if we didn't have the graph, we can ask ourselves the same question, like, can I get a y value or an output that's negative? So if you take a positive number and you raise it to an exponent, can you ever get a negative number? Because we don't have any negative factors, right? If the base is positive, all the things you're multiplying are positive. Can you ever get 0? If you take a positive number and you raise it to an exponent? But you can get positive numbers, right? So we can have anything greater than 0. And we see that on the graph. So you guys are exactly right. Like, it has to be greater than 0. And like Nick said, we have a horizontal asymptote at y equals 0. Because if we look at end behavior as x approaches infinity, our function or our y value gets closer and closer and closer to 0, but it can never be equal to 0 because we never have a factor of 0 anywhere. We're never actually multiplying by the number 0. So our range is 0 to infinity. Which it's convenient to remember that there's a horizontal asymptote at y equals 0. One thing that makes exponential functions a little bit different than like rational functions, which is the other place where we saw horizontal asymptotes, is that when we worked with rational functions, remember we'd have something like we'd have a horizontal asymptote right here. And as x went to infinity, we'd approach that horizontal asymptote. And as x went to negative infinity, we would also approach it. So like we approached the horizontal asymptote on both sides. With exponential functions, we only approach the horizontal asymptote either as we go to negative infinity or positive infinity. The other side just approaches positive infinity. So we don't level off on both sides. We get steeper on one side and we level out on the other. Okay, what's f of 0? It is 1, good. Anything raised to the 0 power is equal to 1, which means that our y-intercept for this function is 0, 1. Now notice that we have a coefficient of 1 here. Right, so there's no number in front. What's f of 1? So for the first two that we did, that is correct. What'll it be for this general one? Just a, good. So that's the point 1a. Knowing that you have that horizontal asymptote and knowing that every single exponential function with a coefficient of 1 goes through 0, 1, and 1a will allow you to graph any exponential function, right? You know that you have to approach 0 on one side. You have these 2 points. You don't have to do any calculations, right? And if you know those 2 points, because those 2 points basically tell you how steep it is. So let's generalize a little bit. So this is a specific situation where our leading coefficient, or our only coefficient, sorry, is 1. Remember yesterday we had an initial value, characteristics of f of x equals c times a to the x, right? We had an initial value of c. So what should that do? Like if I multiply the output of a function by a constant, like when we did transformations, we did like x squared and then compared that to like the graph of 5x squared. What did multiplying do to the graph?
It made it shrunk it vertically.
Stretches it.
Or it stretched it. Yeah,
Mhm.
that one too.
It stretched it vertically, right? It made all the y values bigger by a factor of 5. So remember, it appeared to us that our parabola got narrower horizontally because it was being stretched vertically. And so the same thing should happen here. So transformations are the same regardless of what type of function you're using. So multiplying by a constant here should take a graph like this and just stretch it or compress it vertically. So does that change the domain? If I multiply my output by a constant, does that change what my input can be? Still the same. Will it change my range? So if I multiply by some constant, can that get me below the x-axis?
No.
So that is sort of true, as long as c is positive, right? So as long as c is positive, all those positive values that I got for my output, they're going to stay positive. So if c is positive, then my range is still 0 to infinity. If c is negative, so if I multiply by a negative coefficient, what will that do to my range? What will that do to the graph? To the y values? If you start with all positive y values and then you multiply by a negative. Right, so if you start with all positive y values and you multiply by a negative, you'll end up with all negative y values, right? So that'll just be from negative infinity to 0. So on the graph, that would just have the effect of like flipping that green one And just flip over, so you're just coming up to 0 rather than coming down to 0. And then what about my y-intercept? Is it still going to be at 1? If you plug 0 in. You don't have to just like know the answers to these questions. Like you could plug 0 in and see. I never expect you to just poof know everything. What do you get if you plug 0 in to that function?
1.
So a to the 0 is 1. This is true. So if I, yeah. Right, because of order of operations, like you have to do a to the 0 first, which gives you 1 times c. You can't multiply the c times the a and then raise it to the 0 power. So what's my y-intercept? Yeah, good. Just like we talked about yesterday, right? That's your initial value, is that c. And then, oh, I don't really care what f1 is. It's just a times c, but it's not that interesting as far as characteristics go. Okay. So we have 4 graphs here, 4 functions. 2 of our graphs are increasing, 2 are decreasing. Can you narrow it down? Of A, B, C, and D, which are going to be increasing? B and D, why?
Because if it were A and C, that's like a decimal, so it'd be going for
Right, yeah, these guys, our base is greater than 1, right? And which is going to be which, do you think? So if I have 6 to the x and I have 1.5 to the x, and my options are 3 and 4, what do you think?
3 is B and 4 is D.
Why?
Number or B like increases.
Wait, did you say B is 3
Yeah.
and 4 is D? Thank you, sorry.
Yeah.
I was writing B for B.
3 increases at a greater rate.
Yeah, it's going to get bigger faster, right? Because the base is bigger. So if you think about, for instance, just like a given value of x, like if x was 2, like the y value on graph 3 is always going to be bigger than the y value on graph 2, or sorry, 4, if x is a given value. And 6 to the second is always bigger than 1.5 to the second, right? Or to the third, or the fourth, or the fifth. So that's exactly right. And you can kind of think of it as like steeper, right? Like number 3 is steeper than number 4, or it gets steeper faster. So we can say that because 6 is greater than 1.5, B grows faster. Okay, let's look at these decreasing guys. So A and C have to be decreasing, and my choices are 1 and 2. Which do you think will be which?
7, 5 would be 2.
You think?
I think it's the other way around.
Why?
Choose C.
Why?
Because it's like 2 is increasing at a greater rate, or decreasing at a greater rate.
Mm-hmm.
So therefore it would be C.
Because?
I'm just kind of eyeballing the graph. I don't know.
So there's a couple, like this one's not quite as intuitive, right? Because we want the bigger number to produce a steeper graph. Like that's what it does on the other side, right? So a couple ways you can look at it is if you take like just any x value, like say this one, we have a point here and a point here. Should 0.75 produce a bigger number or 1/10? So 0.75 to any power is bigger or smaller than 1/10 to the same power. Right, a bigger number raised to a power is going to be bigger So then this one has to be A. Like just by virtue of like picking a single x value and saying like the y value has to be bigger if the base is bigger.
Can't you tell by looking at the other part of it too?
Did I do that back? No, that's
The
right.
other side of it.
Yeah, so the other way you can think about it is that, remember we talked yesterday about decay factors and how the decay factor is what's left, right? So if you have 1/10 left versus 0.75 left or 75% left, which one's getting smaller faster? Which one gives you less faster?
C.
Yeah, right? If I only have 1/10 left and then 1/10 of that and 1/10 of that, that's getting smaller way faster than if I have 75% left and then 75% of that and 75% of that, right? If you have more left, you're bigger. So we're getting smaller faster if we're multiplying by a smaller number repeatedly. So 0.75 is greater than 1/10, which makes C decay faster.
The way I was looking at it was, you know how you do the transformations, use the coefficient. If it's a larger coefficient, it stretches on the vertical axis, right?
So
So the inverse of 10, for example, is 1/10. So if you're doing an exponential, it's going to climb steeper with the inverse of 10. Is that making sense or not?
well, you're saying two different things,
Okay.
but the second thing you said is true. That the reciprocal of 10 is if 1/10 is bigger than the reciprocal of 0.75, and therefore the reflection of this graph should be steeper than the reflection of the other graph. That's true. There's the coefficient of all of them is 1, so the coefficient doesn't come into play. We're gonna skip this. It's not really anything to it that we haven't already talked about. We are gonna do this though because this is cool. Although in the first two classes, not everybody really thought it was as cool as I think it is. I'm sure it'll become cooler as you guys learn more about it. So we're going to graph e to the x. We'll use an x value of -2, -1, 0, 1, and 2. On your calculator, we want e to the -2, which is 1 over e squared. You cannot use the letter e on your calculator. Like, you know how you can do like alpha and get letters? The letter e won't do anything for you. So 1 over e squared is approximately like what, 1.14? And e to the -1 is 1 over e. Oh, I can make an e. Come on now. Which is like 0.39? 7, thank you. Without your calculator, what's e to the 0? Good. And then e to the first is, these shouldn't be equal signs, these should be approximately, is approximately 2.72. And e squared is approximately 7.39. Is it a 9?
Yes.
7? 9? Okay. Okay, so let's plot those points. See, we've got a point way down here, one here, 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 and So I'm going to do this really quick because we don't have a lot of time, but we can talk about it more tomorrow. That's a really ugly curve. Pretend it's really pretty. The number E is approximately 2.72. It's like 2.7186, something. But it's an irrational number, much like pi. The reason that we call it E is because it's irrational, which means it's a decimal that goes on forever and never repeats in any pattern, right? So the only way that we can represent it in its exact form is with a symbol, just like we use the symbol pi for the irrational number pi. So when you see E, and this is the reason, like, you don't see people use E as a variable, like in equations and stuff. Like in your textbook, you'll notice they never use E as a variable because E doesn't change. It's a constant, so it's always the same number. And where this number came from is we just talked about how depending on what the base is, the graph of an exponential function can be kind of steeper or shallower, right? So we talk in calculus a lot about tangent lines, which are lines that touch the graph at exactly one point. And we look at the slopes of those lines. So the development of this number E simply came from somebody drawing a whole bunch of, well, they didn't draw them, they did lots of math to figure it out, but there were, you take a bunch of exponential functions, right, and they're steeper, shallower. It turns out that this number, this big crazy number, happens to be the only base which produces a specific tangent line. When x is 0, what's the slope of that tangent line? It's 1. That's only true of this base. Like, you can choose any other base, like, and graph the exponential function and find that slope, and it's only 1 for a base of E, which is where the number E came from. And it actually ends up being a super important number. Remember yesterday how we talked about how, like, our half-life example, like, that model wasn't super realistic because it did periodic growth, where, like, well, decay in that case. Periodic decay where, like, after 200 years, all of a sudden it split it in half, and then 200 years passes and it splits it in half again, rather than taking into account the fact that it's gradual. So using a base of E in our models is what will allow us to get more realistic exponential models that take continuous growth or decay into account. So when we do more application problems in 9.7 and we actually do realistic models of this, we'll always have a base of E. It's what we get when we take a bunch of limits. We need to do one problem before we go, so.
Real quick,
Yeah.
you said it doesn't have the same effect, for example, as pi, like, 2.72 versus 3.17. 3.1416, it doesn't have that same effect upon any coefficients that it's,
I don't know what you mean by effect.
okay, well, if you have 2e,
Yes.
you aren't multiplying 2 times 2.72, or are you?
Uh-huh. E is a
You are.
number.
Okay, at one point I thought you said that it doesn't change.
It doesn't change. The number
Okay,
E is always the
constant
same.
doesn't change, all right.
Correct.
Yeah, okay. All right.
Okay, so your homework tonight is basically just writing exponential functions. The only thing you really need to remember in order to do this is that my pen stopped working. There it goes. Is that the y-intercept of this graph is what? C, yes, right? It's just that coefficient. And so if I'm given the y-intercept of an exponential function, that tells me that C is equal to 0.4, which gets me halfway to my function, right? Like, in order to write a function, I need two constants. I need a number for C and I need a number for A. So that gets me halfway there. That tells me that f of x is equal to 0.4 times a to the x. And then the other part of it, we do exactly like we've done all the other equations that we've written, right? Remember when we wrote quadratic equations we just plugged a number in and we solved for the constant we were looking for. We'll do the same thing here. So we have another point, 350, which tells me that I should get an output of 50 if I use an input of 3. Right, so we plug in our x and our y. This is just like what we did with other types of functions, just plugging that point in and then using what you know about solving equations to solve this. So we'll divide both sides by 0.4, which gives me 125 equals a to the third. How do I solve that? Yeah, we take the cube root of both sides. So the cube root of 125 is equal to the cube root of a to the third, and a equals 5. Even if that was an even exponent, we don't deal with any plus or minuses here. Like if that was a squared and we took the square root of both sides, we don't get like a plus or a minus because a is always positive, right? By definition of an exponential function, your base has to be positive, so you just take the positive one. So our function is 0.4 times 5 to the x. That process goes the same way every single time you do this. We cannot multiply the 0.4 times the 5. Why not? Yeah, order of operations, right? This is a single factor of 0.4 and x factors of 5. If we multiply the 0.4 and the 5 and raise that to the x, that's saying we have x factors of both of those, right? You have to do exponents before multiplication, so we can't multiply those two numbers. If you find yourself getting tempted, it sometimes helps just to put like a visual like multiplication symbol between them if you find yourself making that error a lot. Good? Make sense? Again, all of these behave the same way. You really just have to remember to plug that point in and solve, and you'll get your A. Your homework tonight